These are notes on ion formation. In your book, this is Chapter 7, Section 1. Some of this will be review to some of you, and for some of you this is going to be new. So, in order to understand ions, we really need to understand valence electrons. And we've touched on that, and we've looked at the trends on the periodic table, excluding the transition metals, but we really need to understand what valence electrons are. So valence electrons are electrons in the highest principal energy level of an atom. Another way to say this is they are the outermost electrons. So let's look at what those would be. So let's take a look at sodium here. Here is sodium's electron configuration, and so if we look at the highest principal energy level, that's going to be 3s1, meaning sodium has one valence electron, which is what you'd expect based on the trend. Now remember, this is why all elements in a similar column have the same number of valence electrons, because if you look at the next element down, which is potassium, potassium ends up with 4s1, so that would be the one valence electron. So if you start to notice that trend in electron configuration, that helps you understand the trend in valence electrons. If we look at aluminum, here's aluminum's electron configuration. Now notice when we abbreviate that, it actually helps us to very easily see where those valence electrons are. So aluminum would have 3 valence electrons, the 2 from the 3s and the 1 from the 3p. If we look at germanium, germanium's a little harder now, because if we look at the abbreviation, we have argon 4s2, 3d10, 4p2. Now remember, we're talking about the electrons in the highest principal energy level. So that's going to be these 4p electrons and these 4s electrons, but not the 3d electrons. That's one principal energy, that's n equals 3 instead of n equals 4. So germanium has 4 valence electrons, which also kind of explains why I told you to skip transition metals, because remember, all transition metals are going to end in d orbitals. So there's clearly something else going on there if we don't count that lower d orbital when we're looking at valence electrons. Sulfur then, I wanted to pick something from the far right of the table. Sulfur would be neon 3s2, 3p4, so these are the valence electrons. We have 6. So let's look at our ideas of electronegativity, which is how easily an atom attracts electrons, and ionization energy, how easily you can remove an electron. So ions are atoms with fewer or more electrons than a neutral atom. So here are 4 elements. Go ahead, pause the video, and place them under the headings whether they have a high electronegativity or a low first ionization energy. So go ahead and do that. What you should have gotten was sodium has a low first ionization energy, beryllium has a low first ionization energy, meaning it's easy to remove an electron from them. Fluorine has a high electronegativity, as does sulfur, meaning it's easy to add an electron. They're going to easily attract electrons. And we'll use these ideas for different things as the year progresses, but this can help you understand whether atoms are going to gain electrons or lose electrons. So atoms are going to gain or lose electrons to fill their valence shell. Now take a guess as to whether things with a high electronegativity are going to gain or lose electrons, and the same for first ionization energy. Make a little hypothesis and then continue the video. Whoops. There we go. Atoms with a low first ionization energy will form positive ions, and those are generally going to be metals. Atoms with a high electronegativity are going to form negative ions, and those are going to be most nonmetals. Noble gases don't form ions at all naturally, even though they are nonmetals. So negative ions mean they've attracted electrons, so they have more negative charge. Positive ions have lost electrons, so they have more positive charge, less negative charge. So let's take a look. Sodium, which we know has a low first ionization energy, it's going to lose electrons to fill its valence shell. So it's 1s2, 2s2, 2p6, 3s1. This right there, those are its valence electrons. So if it loses one electron, then this entire shell goes away, which is also why positive ions are smaller than their neutral atoms, because now we've lost that entire third energy level. And you'll notice now we have a full valence shell here, 2 plus 6, which is 8. And we write that as sodium with a superscript 1 plus, meaning sodium with one extra positive compared to negatives. It hasn't gained protons, that would make it a new element. It's lost an electron, but that gives it a 1 plus charge. Let's look then at sulfur. This is sulfur's electron configuration. So it's going to gain 2 electrons, which is going to change this 4 here to a 6, and once again we have a full valence shell. 8 electrons, 3s2, 3p6. And sulfur then, because it has 2 extra electrons compared to protons, ends up with a 2 minus charge, s2 minus. So let's look very briefly at transition metals. Transition metals are likely to form multiple ions, so they're not as predictable. So let's take a look at iron here. This is iron's electron configuration. It's argon 4s2, 3d6. So let's look at that. So here is our 4s2, and so we would, we would have this, and then our 3d6, we've got 1, 2, 3, 4, 5, but there's only 6, so 1, 2, according to Hund's rule, remember 3, 4, 5, 6. So now, if we look at the highest principal energy level, that's 4s, which means these electrons here are the valence electrons. So it's likely that iron is going to lose those 2 valence electrons. It is a metal, so it'll become a positive ion. And so if it loses those 2, we end up with Fe2+. But occasionally, iron is going to lose both of those plus this one up here in the 3d, because then that puts 1 electron in each of the d orbitals, and iron likes that a lot better. So occasionally iron ends up as a 3+ as well. And certainly you can worry about electron configuration. At this level, I'm not going to ask you to worry so much about electron configuration when it comes to transition metals and ions. Once we start naming ionic compounds, I'm going to teach you how you can figure that out, whether it's iron 2+ or iron 3+. So I'll give you different strategies as we go along. Please make sure you watch the next set of notes, which are on ionic compound formation.